Hello, this is Alan Folmsby here in Hawaii, and this is platinum, the nucleus of platinum, magnified 5 trillion times. And platinum has a special effect as a catalyst, and the shape of the nucleus has a shape which could plausibly be the cause of the excellent catalytic effect. One thing about it is that a thin wire of platinum can cause methane to burst into flame even at room temperature. So that's a well-known thing which gold can't do. Even though gold has one more proton, somehow that makes it not be as good of a catalyst. So let's take a little closer look at this. So I'm going to just point out the hook, the ring, and the axis. So down in the bottom, we see a single red dot for a proton. That's the axis of a ring. And the ring makes a hook shape here. These brown dots here go around in this direction here. And that ends up as a line of protons starting up at the top, going down, and then a loop around the axis into a hook shape there. So I'm going to illuminate a little bit from the bottom here so you can see some of the loop on the outside. So in addition to what I was saying about the hook, there's also the outer loop which goes around here, out on this section on the far right here, and it loops all the way around the nucleus without any breaks. So protons tend to form lines of protons, and the strong nuclear force is holding this together in a way that doesn't matter if it's a proton or a neutron. Both of them are treated equally in terms of how the shape and the outline is made. For example, in this picture you can see uranium silhouette, and these are just protons and neutrons in black, and in red are protons and neutrons. So really the shape has nothing to do with whether it's a proton or neutron. All baryons are treated the same. And you see there's the big pyramid on top there with a dilated pyramid onto a red cube of baryons. The 6 faces of the cube have a little pyramid, and then below the cube, red cube, there's more similar to platinum. So going back to the platinum picture here, we see the big pyramid at the top, and we can also take a closer look at the picture of the silhouette of this element. There it is, tungsten. And a little one next to platinum has 4 more protons on it than tungsten. So really, platinum looks a silhouette much like tungsten there. The big pyramid on top. It's pear-shaped, like radon, radium, or barium. So now getting back to this tiny model here, I'm going to just zoom in on it a little more in just a second, right after this outdoor look of the laboratories. Nucleus. Okay, now we're back inside Maui Theoretical Physics Laboratory, and I'm going to zoom in on this camera so that we can see a close-up. Alright, great. So this is magnification 5 trillion times bigger than a platinum block. So if you purchase some, it's very expensive, you know, $1,000 an ounce or something like that. So let's just take a look at, I'll point out some things about that. Once again, we're in closer. There's the axis. Down there, a single proton is on the axis of the hook. And then the hook goes around, starting here, hooks around the axis, outside, and then ends up here, isolated from the third feature, is the big ring, which is all these brown protons up here going in a big loop all the way around platinum. So this is a plausible explanation of why this is a catalyst. Other elements aren't like this. For example, iron on the top left there has one big loop around the front there and a single proton white on the axis. So the coding's different, the opposite here, where white is the proton here and the brown is the neutron. Now you see in iron it just is one on the axis and one loop of protons with 12 protons on this side. So that's different than platinum, which has the three features: the outside loop, the hook, and the axis. Now let's just take another look at the symbol for iron. There's a silhouette for iron there. Simple cubic in the center, 27 protons and neutrons, and on the 6 faces there's 6 pyramids times 5 is 30. So 27 plus 30 is 57, and there's iron 57. Now, I'm sure that this is the correct theory of nuclear structure because basically only iron, nickel, and cobalt, and gadolinium have this shape, and all the other elements do not. So I'm going to now back off and tell you a little about today's agenda. All right, in the theoretical physics, we have the strong nuclear force is gravity. All right, so other people have said similar things, but they didn't know about the conservation of continuum, in which the amount of time growing out of a proton is equal to the amount of space shrinking into a proton for gravity. It's a balance of nature. So I'm on every Monday, Wednesday, and Friday at this time, 20 hours GMT. Today's November 11th, and I have a Master of Science degree. My name's Alan Folmsby, and I have appointed myself to be a theoretical physicist. If you don't approve, please write me a note. Oh, let's see, something just blanked out there. I guess my screen's getting tired of looking at things. Okay, now going back up to the top here. My philosophy is there's many ways to describe a phenomenon, standard science, and I'm offering some new theories. Now, as I was saying, platinum is a catalyst, and the future of electricity depends on knowing why reality works the way it does. It's not just the electrons going through spins and things. The nucleus is very important here, and I'm going into the ab initio, new foundation. In the olden days, ab initio would mean conservation of energy and the Hamiltonian. But I'm going to have a new, from the beginning, negative infinity in the center of the proton, no quarks, and mass equals area theory, an area of continuum liquid. Space is treated as a liquid. And in this theory, 1 kilogram is 1.21 square meters. That is calculated from the well-known standard science, where the proton mass, 10 to the minus 27th kilograms, is equal to the cross-sectional area, neutron scattering cross-section area of hydrogen, well known to be 20.4 barns. So that's where I get this conversion factor. And also, I'm also providing this other number here, the momentum of free space in 4 dimensions, x, y, z, and t. P is the momentum, 7 times 10 to the minus 37th cubic meters per second. Now this is important for the strong nuclear force. And I'm unifying electromagnetism using an 8-dimensional accounting system and the mirror in the proton. And I'm not the first person to say that space is like a liquid. You could look at the paper written by J.S. Hamilton a few years ago, the river model of a black hole. So in the center of the proton is a mirror, and out comes the 4 dimensions of electromagnetism and atomic orbitals, hx, hy, hc, and th. Now these are different than ordinary space in that it's more of a membrane, a spline, where an electron connects to a proton using 2 dimensions, h, x, and hy. Now this sets up a non-crossing law for these membranes, so that the membrane connecting a proton to electron cannot cross another membrane for another pair. These are like different universes that cannot cross each other unless certain things are happening, such as a new unpairing and pairing called the ohm. The resistance is per second. Events per second is how many ohms it is. 1 million unpairings and pairings per second has a high resistance, and 1 billion unpairings and pairings of electron-proton pairs per second is a much higher resistance of ohms. And similar for other laws. Everything is being unified now. The non-crossing law accounts for Lenz's law, the Pauli exclusion class of principles, the up-down spin quantization, radio, and nuclear charge distribution that is set during fusion. So here's a very important point for future electricity. We now know, or I now know, and I understand, and now you're finding out, that the nuclear charges, protons, line up into lines of protons because of the pairing with electrons. And even during fusion, in the center of the sun, electrons are still deterministically paired with protons. And just like gravity, doesn't care if it's hot in the middle of a star. I'm going to define a pair in the future someday. Of course, it's a very important definition. Now, I discovered that ferromagnetism is from 12 protons in iron rings. It has 2 rings of 12 plus 12. Now, the thing is that in the last lecture, last week, I was saying that force is redefined. Mass is affected by gravity, but mass does not cause gravity. And here's why. Isaac Newton had this old equation here, but now I'm replacing the big G. There's Isaac's formula at the top. Force equals G times mass 1, mass 2 divided by the radius squared. Now I've discovered that the G is actually not a mystery of 6 times 10 to the minus 11th something. It's actually the volume of a proton divided by 2 pi, 5 nanoseconds per mass of the proton second. Now the thing is that if you look at this one that Isaac Newton had proposed here, he's saying it's cubic meters per kilogram second squared. But where do they get cubic meters from? All they're trying to do is say acceleration equals meters per second squared, and then the other two powers have to be canceled out, and the r squared is in the main formula for force. So to cancel that out, they had to throw in a couple more powers of distance to make the units all work out. Now I've gone beyond their simple lumped functional model, and I'm defining articulately that volume is the volume of a proton. So they didn't realize this cubic meters they were talking about here really is the volume of a proton per kilogram second squared. There's the kilograms by proton. And second squared is 5 nanoseconds and another second here for the test that was done. So anyway, this shows that the new formula is right here. Force, instead of Newton's formula, this one can now be used for the strong nuclear force once we have now articulately said that here the big N is the number of baryons in the Earth, for example, and the little n is the number of baryons in a satellite. Now what we're doing is we're multiplying the big N times the volume and the little n times a mass, nm. So in other words, the small one is being affected through its mass, and gravity is being caused by the big N and r cubed, the volume. All right, so anyway, this shows where that comes from, and I wanted to show you the gravity volume theory. Oh, here it is. Gravity volume theory, because this is what all this is based on. And you know, we could just pause again for a message from our sponsor. Hello, it's Alan Folmsby here in my front yard. This is where I discovered the shape of the iron nucleus. All right, we're back from our break here. Thank you very much. 24 seconds later, we have the gravity volume theory. And the thing about that is it's a simple equation on the left here. N is the number of baryons in a planet. V is the volume of a proton. Tau is 5 nanoseconds. Or some time constant that we have to calculate. If you don't think it's 5 nanoseconds, I'll show you how it's done. Z is the height fallen. You drop a rock for 1 second, and the rock falls 4.9 meters. A is the area of the Earth. Okay, now the thing is that this is momentum on the left and momentum on the right. It's called the momentum of free space. All right, so memorize that. Let's see, I'm going to jump back up to my agenda here. All right, the river, the mirror, Lenz's law, we went through that. Now, force, yes, we talked about force. Now, the strong nuclear force, of course, is not based on Coulomb's law, but rather it is gravity, I propose. This is the proposed theory. So, if I talk like it's a fact, you know, pardon me. I'm just saying it's a theory that I happen to believe in as being possibly true, or it could be wrong. So anyway, the strong nuclear force is gravity with the proton radius as the curvature of space, and that makes the mixed partial derivatives very important, more important than other kinds of simpler far distant gravity. When you get close, times fifth derivative does the strengthening of the force, so it becomes a strong nuclear force. It could be 10 to the 46 times stronger than gravity because of the higher derivatives. And I'm going to be looking at dt dz, where the change of time thickness as a distance exiting the nucleus or entering it. So suppose a proton is approaching the nucleus of something, and time is getting denser as it gets near the gap. For example, in iron there's little gaps between the hexagonal close pack types of things. So, for example, in this picture, there's little gaps between the protons and neutrons here. The green protons and white neutrons are really hexagonal close pack on the surface of the nucleus, but in the core it's cubic. And I believe this is true because if you had placed a hexagonal close pack in the center of these nuclei, the surfaces would have been covered with a cubic lattice, which is more vulnerable to collisions and decay and things. Okay, now the thing is that time is coming out of these baryons radially at the speed c, and space is draining in through the gaps and onto the surfaces. But imagine at the very center of one of these nuclei, there's still a lot of time being emitted from the center of the core, and it has to escape through the gaps. It cannot go through the baryons. It has to curve around the outside. So that's the same time the space is also coming through the gaps because it cannot penetrate the baryons. So there's a hydrodynamic flow using 4 dimensions right there, and I'm going to be modeling that using partial derivatives, mixed partial derivatives. And so, you know, you can mix anything you want. The speed of space as a function of the distance from the nucleus, or dx dt, the velocity of something. And I think it would be good to go back to my notes here. So like I was saying, dt dz, the change of time density as you depart, and there's other partial derivatives and mixed partial derivatives of time and space curving around the protons and neutrons, causing much greater changes in acceleration, which is the third derivative of distance. So I'll just draw some pictures here. Oh yes, I'm adjusting my picture paper. All right. Oh, here's my pen, and I'm going to be talking about the curves around a nucleus. So we have one nucleus over here, and some more, and there's a gap between them. Let's say it's cubic. And then there's a hex one over here. So you can see this, the gap over here is much bigger for a cubic lattice than the gap over here for the hexagonal close pack. So that the cube has to be armored against destruction, and the only surviving elements are the ones that have plenty of armor on the faces of the cube. Now, the strong nuclear force will be coming through as something approaches. Like suppose now we have another proton approaching here. it's moving in towards this nucleus. And time is coming out of a small gap. There, time is emerging out, but it's coming from 4 of these things, so it's thick. 1, 2, 3, 4. Inside the center, so now time is extra thick. So this goes to higher derivatives of time. Space is going in through gaps, and it has the speed of space, which I'll define in a few minutes on my pictures of. Anyway, what I'm going to be doing is derivatives, not only just dx dt. It'll be things like this. Let's say x equals x0 plus vt plus g t squared plus g of z and t cubed. So there's a higher derivative then. So like I was saying, an even higher one could be g of z and t fourth. So all this it's a function, the acceleration g is a function of how far you're away, and that is a function of the time, which is a function of how far away you are. So you have to use the chain rule to have the changing time thickness accounted for in a higher power of magnification. And I expect that we could adjust the various constants and derivatives so that these types of nuclei could have a strong nuclear force based on gravity. All right, now I have published a paper just to change the subject a little bit here, and let me zoom in on this a little better. This is in the Journal of Nuclear Physics, March 2019, Magnetism from Iron's Nuclear Structure. And I have some rules in here for how the nucleus is put together. So let's take a look at the rules used for sphere stacking, as the strong nuclear force pulls everything together. All right, rule number 1, a cube of baryons is designed at the center of the nucleus. Now, in a huge collection of baryons before the Big Bang, say there was trillions of baryons all squeezed together with no space other than what has expanded during eternity, say a billion times smaller than the radius of a proton is the space separating the protons. And they're all pressing together. You might expect either a cube to be the densest packing of a vast collection of neutrons, or a hexagonal close pack. So anyway, I found that the cube will actually form on its own. Now, inside the cube, the protons are far from each other, as if they repel each other. And at the center of the cube, protons are sparse. So I go and give a lot more rules about how to put the things together. Protons form lines of protons. And then we see that you get the little pyramid of lithium forming over the iron. And so I'm going to go back to the message from our sponsor again here, and set up the next conclusion. We have 2 minutes left to go. I'm running into my concluding remarks now in this half-hour program. so that is going to start. Now, all right, so like I was saying, you got the gravity volume theory. Gravity volume theory was defined clearly today. NV over tau equals ZA over 1 second. Momentum on the left equals momentum on the right. Now, what it's saying is that it's a fallen shell. ZA is the fallen shell of what could potentially have fallen. In other words, if you had picked up rocks on 1 million locations around the Earth, they all would have been existing in a similar shell around the center of the Earth, where they will fall Z meters, and the area of the Earth is A. If you multiply an area times a height, that's the volume. It's like an onion skin of around the Earth. That volume in a second is equal to the volume of the protons and neutrons in 5 nanoseconds. That's the basic concept of gravity volume theory. The volume of baryons is affecting the volume of the space around it. On the left, we see the volume of all the baryons in a planet in 5 nanoseconds is equal to the volume of the fallen shell in 1 second. That's the gravity volume theory. And the gap theory of the strong nuclear force was explained. Let's see, Blender 3D software gives you some hydrodynamic boundary conditions of nuclear space-time. You can go to Thingiverse and look at the 3D models and create your own hydrodynamic simulations. Blender supports physics. They have built-in things for flows of smoke and things. Now, the question is, why is there a simple cubic lattice in the center of nuclei? And the answer is survival. The armor over the cube has small gaps. The cube has bigger gaps, so it has to be armored. And it survives because it's a face-armored cubic. And I want to overemphasize that the gap for the strong nuclear force releases a thick time, so you get double derivatives, so that not only like acceleration is the second derivative position, but also we're going to have the third derivative and the fourth derivatives because of the thickening of time very close to the gaps of a nucleus. These ideas have not been approved by educators. My name is Alan Folmsby. Thank you. I'll be back on Wednesday. Same time.
Hello, it's Alan Folmsby here in my front yard. This is where I discovered the shape of the iron nucleus.